Why is the sky blue? One of the most fundamental questions of life, quite frankly, not just astronomy class. And, we've all been introduced to this concept along the way, probably at different levels of sophistication. Some of you know already why that's true, and some of you have no clue whatsoever or have a very wrong understanding of it. So let's fix that. I'll give you a hint. The sky is blue during the daytime. It's not blue at night. Guess who the culprit is? Yeah, it's the sun. Now, nobody would say the sun is blue, nor would you say that the sun's color is, well, it's the same thing, yeah, is blue. But the sun does send us blue light. The sun sends us all the colors of the rainbow, which you can tell quite easily by sending sunlight through a prism, right? And we see the rainbow of colors projected on a wall or on a screen. So, it is the sun's blue light, which is the minority of its light, that actually causes our sky to be blue. But there's much more to it. So let's discuss. Let's do a little drawing here. I'm going to make the earth green. And if you want some continents, sure, I'll give you some of those too. Definitely not our continents, but somebody's continents. And we'll give you a very thin blue atmosphere around it. Now, believe it or not, on this scale, this blue atmosphere is way too thick. If the Earth was this size, about the size of a softball, then the Earth's atmosphere would be about the thinness of tissue paper, literally, extremely thin, barely there. And yet that's what protects us from the harmful radiation from our sun. It's what causes life to exist, and if we destroy it, we're all done. So we better take care of our atmosphere, that's for sure. But above it, I'm going to give you a sun. And the only reason I'm drawing this in red is because I don't have that many colors as a choice here. Our sun is primarily what color? Yeah, we talk about it being a yellow sun or a yellow star. And the sun gives me all the colors of the rainbow, but it sends me more yellow than any other color. So that's why it looks overwhelmingly that color. The color your eye recognizes the best is that yellow-green color that Caltrans workers wear as stripes on their vest, or a tennis ball color, yellow-green. That's the sun's predominant color, and that's why you see it the best. You grew up underneath this sun. If you'd grown up underneath a different star, guess what? You would see a different color the best. But that's when we all really, really notice. So there really should be a green-yellow sun, but again, I don't really have that capability, so let me just label it. That's the sun. And the sun sends me all the colors, so red, orange, yellow, green, blue, indigo, and violet. Do you know your Roy G. Biv? Yeah, Roy G. Biv. Just standing for all the different colors. Roy is red, orange, and yellow. His middle initial, G, is for green. And the Biv is blue, indigo, blue jean color, and violet. Although these days you're right, blue jeans come in all the colors, even non-blue. But if you've heard that phrase before, then yeah, that's the visible colors of light. And I can, of course, draw red, so I'm going to use the red marker for red. And the sun's red light does this. It comes in, and it knifes right through the atmosphere like a knife through hot butter, straight through. Has no troubles getting through our atmosphere. And you're thinking, oh, that must mean that red light is more powerful than the other colors. Counterintuitively, it is not. Red is actually the weakest in energy of the visible colors of light. So it has nothing to do with energy or strength. It has everything to do with wavelength. The wavelength of red light is long. So I draw you a wave train over here. That's what we call that, a wave train. And you know about wavelength, the distance between two peaks, I'll bet. And wave frequency, how many of those peaks go by a certain point in a given amount of time, like 1 second. Frequency and wavelength determine what color of light you're looking at. And blue light, and violet especially. I got violet, so let's use violet. But violet light is very short-waved. And because of the shorter wavelength, more of those crests of the wave go by a certain point in a given amount of time, so its frequency is higher. And like a teeth on a saw, the more there are per inch, the more damage it does when you actually, saw it back and forth. This is more energetic than red light, much so. But blue and violet come in, and since I'm dealing with why is the sky blue, I'll use blue. Blue light comes in, shorter wavelength I should have made them, I'm trying. And it does not knife through the atmosphere like a knife through hot butter. It gets stuck, it gets absorbed, then re-emitted, absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted, you get the idea. And blue light bounces all over the place, absorbing, re-emitting, until finally it works its way down to the earth. So if you look directly at the sun, please do not. You would see copious amounts of red and even orange, and yes, yellow. The Roy would be very predominant if you look directly at the sun. Don't do that. But when you look in any other direction, all we see is the scattering of the shorter wavelengths of light, the blues and the indigos and the violets, making the sky look extra blue. And it's over here too. I'll make these short wavelengths. They also get absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted. So if the sun is above your horizon, then we see all that blue scattering of light by our atmosphere. And that's half of the reason. It's all about the wavelengths of light that are, striking our atmosphere from our sun. But it's also about the molecules of air that we breathe. When you take a lungful of air, 78% of it is not very helpful to you. It's nitrogen with an N. N2, the nitrogen molecule, we say molecular nitrogen, is two nitrogen atoms bonded to each other, like so. And of course, your body doesn't care about nitrogen. It comes in and it goes out, right? Inhale and exhale. But thank goodness, 21% of the air that you're breathing is oxygen. And it's molecular oxygen, O2. Same thing, two oxygen atoms doubly bonded to each other to make up the oxygen molecule. Now, I drew them this way on purpose. What do you notice about N2 and O2, the molecules? They're about the same size. Guess what else they're similar in size to? The wavelengths of blue light. That molecular size is about the spacing. I know that's a purple, so I can make blue a little bit longer. But the molecular spacing of the oxygen molecule is very similar to the distance between two crests in a blue wave. And therefore, they love blue light. Blue light comes in and tickles them, and they absorb it, and they get a little excited, and they turn around and they spit it back out in a randomized direction. Of course, we don't say spat, but we say re-emitted in a new direction. But this happens over and over and over with every single nitrogen and oxygen molecule that it encounters. So all the blue light is busy, bouncing all over the place. Scattering is the proper term for that. And if you've had a little bit of physics, you know that the sky is blue because of Rayleigh scattering. Yes, the fancy word for the guy that discovered why this is happening. Yeah. So why is the sky blue? It's really two big things, isn't there? Number one, it's the plethora, the array of different colors of light the sun sends us, all of different wavelengths. And the fact that one of those colors has a wavelength that's about the same size as the molecular size of air that you and I breathe, nitrogen and oxygen. Nitrogen makes up about 78% of all the air that we breathe. Oxygen makes up about 21% of all the air we breathe. Sum those two together, and what do you get? 99, yes. Almost all the air we breathe is nitrogen and oxygen. When an athlete is winded and they go to the bench, what do they do on a very hot day? They start sucking on pure oxygen, don't they? Because that is 5 times the dosage of normal. You get to that state of oxygenated 5 times quicker if you're breathing pure oxygen. All right, so just the scattering of sunlight. And when the sun dips down below the horizon, and of course there's no more scattering of light, all you see is, of course, the absence of light. You see darkness, don't you, at night? So be prepared to explain that back to me, why our sky is blue. And why are we even talking about this? We're talking about it because we've been introduced to a reflection nebula. Yeah, probably the Pleiades is the one we just talked about. Or maybe it was the reflection nebula that makes up half of the Trifid Nebula, M20. But here's a photograph of the Pleiades, or M45, up close. And all that blueness that you see there is blue for the same reason that this is blue. It's not that there's a whole lot of oxygen and nitrogen molecules out there around these stars. Rather, it's dust particles. But the dust particles, which are simply multiple atoms bonded to each other, are about the same size as these two molecules. And guess what? They do the exact same thing. They absorb, re-emit, spit it back out. Absorb, re-emit, spit it back out. Blue light in all different directions. And these stars are all blue-white stars, which give off copious amounts of bluish-white light. So they have even more blue light than our sun does. And therefore the scattering of that blue light is very, very evident, isn't it, when you look at these blue-white stars surrounded by these dusty cocoons out of which they were born. So there's the tie-in to reflection nebula and why our sky is blue, but very similar reasons. Okay? Please know about the molecules of air that we breathe. Please know about the different wavelengths of different colors of light, and realize that our atmosphere is very, very thin. And even though it's the scatter of all these things, without our atmosphere, we're all dead. So do your best to protect it as well.